Okay, so I've just proved that Sn is generated by pairs ij. Basically by showing that any long cycle is a combination of transpositions. I'm going to prove something even better. I'm going to prove that it's generated by the set X, where X equals the set 1, 2, 1, 3, up to 1n. Oops. 1, 3, up to 1n. Well, all I've got to do is prove that if I get a cycle ij, I can just write it in terms of a combination of this set here. So I'm just going to write 1i, 1j, 1i, 1j, 1i, like that. So let's just check. What does this one do? 1 goes to I, which goes back to 1 again. There you go. So you see, you do this one here, 1 goes to I, and then it misses it out, and then that's 1's there. What about I? I goes to 1, which goes to j, which is what we wanted. What about j? J goes to 1, which goes back to I. J goes to I. If notice that if I equals 1, then this cycle just sort of collapses in on itself, and we've just got 1j, which is correct as well. And if j equals 1, the middle one just disappears. If j equals 1, yeah, if j equals 1, we get 1i, 1i. So what happens here? If j equals 1, then 1i, 1i. So 1 goes to I, which goes back to 1, so it fixes it. I goes to 1, which goes back to I again. So if j equals 1, bugger, what's gone wrong there? Sorry, a bit of a glitch there. If j equals 1, of course, they're not equal, because we've got 1i, 1i. See, these things can get pretty confusing, so it doesn't hurt just to go through it again. If j equals 1, then this permutation is the empty permutation, but it doesn't matter, because look, what we're trying to do is show that that is a 2 cycle. And of course it is, because it is a 2 cycle, so we've still got it. Okay, so just refreshing what we've said, we've got x equals 1, 2, 1, 3, up to 1n, and the group generated by that set X, where X equals 1, 2, 1, 3, up to 1n, equals the symmetric group on n elements. So we've got a set of n minus 1 generators. So we're getting it simpler and simpler and simpler. And I'm going to stop there.